Interesting.
Yeah.
Okay, it's 2:40, so we can start. So let me formally introduce to everybody to in the audience, Professor Roger Wattenhofer. So I'm going to read out his biography, okay, which is long, but I'll quickly read it out. So Professor Roger Wattenhofer is a full professor at Information Technology and Electrical Engineering Department, ET at Zurich, Switzerland. He received his doctorate in computer science from ET at Zurich. He worked for multiple years at Microsoft Research in Redmond, Washington, at Brown University in Providence, Rhode Island, and Macquarie University in Sydney, Australia. So Professor Roger Waterhofer's research interests includes variety of algorithmic and system aspects in computer science and information technology. For instance, in distributed systems, in positioning systems, wireless networks, mobile systems, social networks, financial networks, deep neural networks. Wow, that list is long. Yeah, he's got wide variety of interests. He published in different communities. Yeah, that is really interesting. He published in distributed computing and networks also. So he publishes in top conferences, POTC, SPA, DISC, and distributed computing. And similarly, he's publishing in SIGCOMM, Mobicom, Census, IPSN, and networks. So really interesting. And not only that, he also publishes in algorithmic theory like Stock, Fox, Soda, and also in recently machine learning, NeurIPS, ICLR, ACL. Wow. So I wonder if there's any field where he's not published, any top conference. Yeah, so continuing, his work received multiple awards. The prize for innovation in distributed computing for his work, okay, in distributed approximation, very interesting. And he's also published a book on blockchain, which is very popular. So it's called Blockchain Science, Distributed Ledger Technology, which has been translated in multiple languages like Chinese, Korean, Vietnamese, and etc. Yeah, we should wait to see for it to be published in Indian languages soon, maybe on his request, Hindi and even Orissa, other languages. Okay, so without further ado, let me give it. So, Professor Roger, you can start.
Great, thanks a lot, Satya, for the nice introduction.
Yeah.
Would of course be great to be in India. Actually, I love to come to India from time to time. It's very exciting to me, but unfortunately now we have to do it from here. So I'm going to talk about graph neural networks. I chose this topic because I looked at the conference website and I saw that you have this combination of the two topics, distributed computing and artificial intelligence. And I think this topic is somewhat between the two, maybe similar to Philippas when he thought about what to present. So basically, this is a slide I stole from your website with the keynote speakers only. But so I'm part of those guys here. But my talk is actually going to be somewhat in the middle between distributed computing and artificial intelligence. Okay, so I hope it might be interesting even for both sides. All right, actually for marketing reasons, I renamed AI to ML so that I can make a little joke at the beginning. We'll see the joke as the next thing. So when I think of distributed computing and machine learning, usually I think, computer scientists think these things have not much in common, okay? But I would say they have a lot in common, actually. And my talk is going to be about that a little bit at the beginning, so what they have in common. And here's my little joke. You also can look at DC and ML and have kids at home, teenage kids, and what they would think of when I say DC, ML, they would think of DC, the comic, universe, so to speak, and Marvel, like ML, the other comic universe, right? So they're very similar to distributed computing and machine learning in the sense that for, people who are not into superheroes, DC and Marvel, they're very, basically the same thing, right? The same as for people who are not in computer science, they might think of distributed computing, machine learning as basically the same thing. But of course, if the people are inside, right, they might think of that these are very different things. And the analogy goes on, I would say, if you look at the two universes of the superheroes, so the DC side is more like a god-like universe. So the heroes there are more like gods or half gods, and they have like really superpowers, whereas the Marvel universe, it's more like real humans and not, gods, but real humans who happen to have learned some special force, so to speak. I should also say that that the Marvel universe is much more popular. I think they have much more sell much more movie tickets than the DC universe. So that's maybe also true in these days when you think about distributed computing and machine learning, that one is more popular than the other. Okay, so that was my little joke at the beginning. So let's now get a bit more serious. I'm going to tell you a little bit what graph neural networks are. And I'm going to make this easy. So maybe for the people who are coming from machine learning side, they are mostly interested in the connection to the distributed computing side, which I'm also going to tell you. And for the others, I guess it's a bit of an introduction also at the beginning of my talk. So graph neural networks. Basically, for the conference with a student of mine, Paul Andras Papp, we wrote a little bit of an introduction. So if you want to hear more, if you want to know a bit more details than what I'm going to talk about here in my talk, you can look at this introduction to graph neural networks from a distributed computing perspective. So what is this graph neural network? So it's sort of doing graph computations together with learning. And it has many applications. And here are some applications. So for instance, one application on the top left might be social networks. We might want to figure out what role people have in a social network by not developing an algorithm, but to tell about some of the roles of people, and then maybe the other people can be inferred by sort of a learning trick. It's also used in recommendation system. It's used in the molecule domain when you want to recognize molecules or make new medicine, and so on, Q&A systems and so on. There's many, many applications. Let me show you one application with a little video. I'm not sure whether this actually works so well with the video, but let's hope for the best. This is not by our group. This is by some other people. What they have is they train a graph neural network to simulate physics, essentially. So on the left-hand side, you have a very complicated physics simulation. And on the right-hand side, you have what the graph neural network kind of just looks at the physics simulation on the left-hand side, and then it tries to, with very simple rules, tries to do that. So it is a graph because you can see on the right-hand side barely, but you can see that you have little particles basically, and the particles are like the nodes in the graph. And then the particles influence each other. And then you basically learn gravity by saying, you know, what does my particle do over time? So I stole this video from YouTube. You can find it there easily when you look for graph neural network and simulation. Let's continue here. So that's, you know, those are typical application examples. Now let me tell you a little bit about the difference between distributed computing. And when I say that, I mean the message passing kind of distributed computing, not the shared memory kind that Philippe was talked about mostly. So in the distributed computing, in the message passing world of distributed computing, we have usually a little network. We have nodes which are connected by edges. So here I have a picture. So here I have a node here, which is connected by an edge to, or by 3 edges actually, to other nodes. And these nodes are communicating with each other by sending messages. A popular model is the so-called synchronous model, where all the nodes would send messages to all their neighbors and then receive the messages from their neighbors and do a little bit of computation and then go into the next round. They send again, receive again, do a computation. So if I want to show that, there's a little post-it here on the right-hand side, would look something like this, that in every round, every node of the system sends a message, receives then the messages which were sent by the neighbors, and then computes something. You can see that this node here and this node here cannot directly communicate with each other, but they would basically communicate with each other through this intermediate node. So in 2 rounds, these 2 nodes basically can also communicate with each other. So that's what we think of distributed computing problems. And I'm going to tell you a few more things in another slide. But let's first look at graph neural networks, what they look like from a high level point of view. So the slide looks very similar. In fact, it's almost the same, right? So the nodes communicate with neighbors by sending messages. And again, in synchronous rounds, every node sends a message to its neighbors. Okay, so basically if I put the post-it here, it's the very same thing. In each round, every node sends a message to the neighbors, then receives the messages from the neighbors and computes something. So far it's exactly the same thing. And there are a few differences, and let me show them. So again, I stole the slide from you guys here, the DC track and the ML track. And we have the common thing, which is marked here with the post-it in the middle, that we have the send, receive, compute cycles that both these systems do. I would say, of course, machine learning is broader than that. They have other kinds of systems which don't work on graphs. This is only about the graph neural networks part of neural networks. And the DC part is also broader than this. They'll have also other things beyond graph algorithms, but at least in this case, they touch. So what's the difference? The difference is in the DC track, the researchers, they design algorithms, right? They have a problem, and now they try to find the best algorithm. They try to find a way how the messages should be exchanged, which is in some sense the optimal way to solve a certain problem. So it's like a godlike algorithm, almost like a godlike designer. If we come back to the analogy of the DC universe for comics, that the algorithms are somewhat like godlike and designed. Whereas on the ML side, of course, the algorithms are learned. So it's like the humans who have to learn some tricks, right? Like in the Marvel universe. Okay, what else is different? So in the distributed computing track, or on this side, the nodes usually have IDs. So the nodes have values from 1 to n or something like that, so that they know who they communicate with. So that's a specialty from that side. Whereas on the machine learning side, usually the nodes don't have IDs. They have something like node features. So they, what is a feature? It could be something like a color of a node initially, or it could be just the input of the node. Let's say if you have a social network, it could be the name of that person, which is there, which is like a, an ID almost, but not quite. So that's a difference, I would say. Usually when we say the nodes have features or the nodes don't have IDs on the ML track, this is also known on the distributed computing side. This is known as anonymous networks. So maybe you, I've done some work in that as well. As such, I pointed out I've done work in almost everything, but that's also something I've tried at some point. You can think of it as anonymous, an anonymous distributed system. Well, in the distributed computing, we usually can have the node send individual message in each round. So we can say if a node wants to send something to its neighbors, then it can do that actually, and can send different messages to different neighbors in every round. Whereas in machine learning, usually this is not done. Usually you cannot send individual messages. You send the same message to all the neighbors. And you don't even receive all your neighbors' messages individually, but you receive just an aggregated message. For instance, the average value that the neighbor sent you, something like this. Okay. Now, this is also to some degree known in distributed computing in some niche area of it. For instance, I once wrote a paper which was called Stone Age Distributed Computing, just to mention my own stuff, but also cellular networks, cellular automata might be part of this track, I would say, where you don't get individual messages from your neighbors, but you just get a summary of what they think to influence your next round state. And then finally, I would say the main difference between the two tracks is that in distributed computing, we usually try to solve some network or graph problems like coloring the graph or routing messages through the graph or stuff like that. So we try to solve classic graph problems, whereas in machine learning, usually it's mostly about classification or regression. So we try to find, what's the right value for some node with regression. And mostly really they do graph classification. They want to know what type of graph do we have here for the whole graph. They want to classify the graphs. Is this a graph which is a tree? Is this a graph which is not a tree, for instance? Or they try to classify the nodes. As I said before, in social networks, they might say, what type of node is that? Is that a man or a woman, or is that somebody from India, somebody from the US, whatnot. So those are, I would say, the main differences between the two areas, mostly the last one, but also the upper ones. So let's go a little bit into more detail. So this is mostly from people who are familiar with distributed computing. I want to explain a bit more what graph neural networks, what they do and how they look like. So as I said before, these are basically message passing graph neural networks. So you have a graph, a network given, like the node, the network here. Let's look at this particular node V in the center here for a moment. And what the node does is it aggregates the information its neighbors have. Okay, so all the neighbors might have some information, some message basically. Usually it's just their last state, the current state that they are in. And now the node V learns an aggregate of this. When I say aggregate, then I really mean you have the state, the information of the other nodes. This could just be a value, basically. For all the neighbors, you have one value, for instance, or a vector of values, for instance. That would be possible. And then when you say you aggregate, you could take something like the sum of those values, or you take the mean of those values, or you take, let's say, the maximum value would also be possible. So those are typical aggregate functions, exactly those three, I would say. Almost all the literatures in graph neural networks just aggregates the neighbor information with these three functions. And now that's the first part. So that's what I call A of V here. And then the node V itself updates its state with another function based on its previous state. Okay, so that's the previous state of the node V and the aggregate of its neighbors. Okay, so those two things go into the function and that gives you your new state, okay, for the next round. Now this state you would again tell your neighbors about. Okay, so this updated state of you basically goes into the aggregate function of your neighbors for the next round. Okay, so you always aggregate your neighbors, and then you have this function you compute for yourself with your old state and the aggregate, and then you tell your neighbors what your new state is in the next round. And you do this for a few rounds, usually for a given number of rounds. So the machine learning engineer, so to speak, decides how many rounds this should go on until it should stop. I have one more slide here to explain this a bit. So what we basically, this is really for people who don't know much about machine learning, maybe have heard of it a little bit, but maybe don't know too much about it. For others who have seen this before, of course, this might even be a bit of a simplification. So we look at just node V here, and we have a 3-round algorithm. So we communicate for 3 rounds. As I said, first you take the node that it starts with. It could be just empty information. It could be every node starts with the same state. And then you input this into this function. And you also input this aggregate of your neighbors. So this is maybe the sum of what your neighbors tell you. Okay, so this is not really mathematical here. It's just something to remind you of the previous picture. The sum of what your neighbors have as a state. You put this into a function and then this gives you your next state for node V here. And again, you do the same thing. And again, you do the same thing. And then after 3 rounds, node V is in some state. And that is the output of your algorithm. Okay, so this might be for something to classify nodes. You want to classify what type of node you have. And that gives you, the outcome of that. For instance, man or woman could be the outcome here. While this function, the aggregation function, is usually a very simple function, it's usually just something like the sum or the max or what I said before. The other function that I have in my little box here is usually a neural network. Okay, so you take all the input values here. Maybe the value of V could be a 2-dimensional vector, and then you have 2 values as inputs. And maybe, maybe it's not just sum or max or mean, maybe it's all 3 of them and you have 3 values here from your neighbors. And that is going through some sort of neural network. And in the end, maybe I should say this was 3 of them and this was only 2 of them down here, then in the end, you know, the new state of V is again this vector of 3 nodes in my picture here. So that would be how I update the vector or the state, or sometimes the machine learning guy says embedding, but I don't like that word so much, but let me just say it once, of this node to the new state in the next round. And you do this 3 times, and then you get the final state here. And now, first, all these 3 networks are basically the same network, okay? So no matter which round you do this, you apply the exact same function usually to the nodes. And you do this for all the nodes in parallel. So not just for our node V, but all the nodes operate with the very same network. Now this network is initially unknown, okay? It's we don't know what this is. This is something we have to learn. This is not something we program. Well, we could program it. We could say exactly how this network should, change the input to get to the output in such a little network. But we think of it as unknown. We think of all the values in this network first to be just random values. So the output will be pretty much random. So if you have some node, some graph, and it has some input at the beginning, what comes out at the very end here, if you do this 3 times, is basically a random value. But then you say, well, I don't want a random value. I want really, I train with known data, and it should really be this vector, let's say, in the output. And then what you do in training is backpropagation, that you change the weights in this network such that the output more closely matches what you want as the output, okay? So that's the idea. You say, well, if something came out here with the random values, which was maybe 0.7, 0.1, 0.9, you would say, you know, the last value here was really very far off. So we should change the weight of this node to make that. And maybe because of that, we should change some other nodes. And that's called backpropagation. And that's kind of the holy grail of neural networks, that you can do backpropagation. Well, one of the main results they have. And then you can quickly learn what the correct weights are. All right. So that's a little bit of an introduction to neural networks. Now, let me come to the main talk of my main part of my talk here. I want to understand the limitations of these graph neural networks. And there's a core theorem here. It's a bit a heavy slide. I apologize. This is the Weisfeiler-Lehman test for graph isomorphism. So that's something that came up many decades ago. They wanted to understand whether 2 graphs are the same graph, essentially. This is the graph isomorphism problem. It's a complicated problem. So people have tried to solve this well for a long time. And this is one of the cornerstone results in graph isomorphism testing. So what you do there is you have a graph given, and now you give the nodes some labels. And in my example here, which I stole from the internet, it's not a very good example. I don't like it so much. But in my example, some nodes have original labels A, and some nodes have original labels B. And one could say all the leaves in this graph, the nodes which only have one neighbor, they are A, and all the nodes which have more than one neighbor, they are B. But I would say here, one could also distinguish those 2 nodes, right? One could say this is a node, the B prime, I just called it B prime now. Node, it has 2 neighbors, whereas the B node, let's say, has 3 neighbors. So whatever I can distinguish based on the graph information first, at the very origin, I will distinguish, and I will say these nodes are in different states. And now I'm going to relabel the nodes for some amount of rounds. In particular, I'm going to look at their neighborhood. You can see, for instance, if you look at this node here, the node A here, it's called A, and it has a neighbor which is called B, and I'm going to give it a new label. All the nodes which have exactly the same circumstances, they are node A and they have a neighbor which is B, they get a new label, okay? In my example here, they would become C. Also, this is without the prime. This is the version without the prime, where both nodes B have the same label initially. And you can see some nodes now become C, But these two nodes, the two B nodes, now can definitely distinguish themselves, because the one which becomes D here is the one which had a B neighbor and an A neighbor, one of each. And the one which becomes E had, as it is written here, two A neighbors and one B neighbor. So they can really distinguish themselves because they have a different situation, a different neighborhood, right? But the nodes which have the same neighborhood cannot distinguish themselves. And if you take the original graph, then you can see that the C guys all had the same neighborhood originally. They all were of this type. They all had were A and had a B neighbor. And so they became, let's say, C. Just call it C. It's a random name. But if you do it again for another round, you can see that we can distinguish more and more nodes. And actually all the nodes are now distinguishable except those two, right? The two G nodes now, they are not distinguishable after the next round. Because, well, they will never be distinguishable because they have the same neighbor. And apart from that, they're exactly the same, right? And they are, well, they're also the same that way. Since they have the same neighbor and they have the same value all the time, they can never be distinguished no matter how many rounds we do that. Now, the Weisfeiler-Lehman test basically says how easy it is to distinguish nodes. If we want to use it for graph isomorphism, what we could do is we could run the Weisfeiler-Lehman tests on two graphs, on two different graphs. And then after that, we know that all the nodes which have the same label in the two graphs, they are potentially the same. There's very few of them. Let's say if we have to distinguish this graph from another very similar looking graph, then basically we just have to check whether the H node and the F node actually they all connected to the same thing, and the G nodes look like this. So it makes it much, much easier to understand what's going on. So that's this classic test here. I hope this was understood. So why is this important? Why is this interesting? So now we can look at graph neural networks, and I have here two graph neural networks. And I would argue if you run a graph neural network, if you run this neural network computation on such a graph, then you ask yourself, what are the limitations of such graph neural networks by using this Weisfeiler-Lehman test? So for instance, here I have two graphs, and these two graphs for us look very different, right? Because one has just 4 nodes and the other one has 6 nodes. So they're very, very different. But if we do a graph neural network on this, as I said, the first thing is you take the node and you take the information of your neighbors. So you take some aggregate function of your neighbors, but the very best you can learn is basically that you have 2 neighbors, depending on what kind of aggregate function you do, that you can learn that you have 2 different neighbors. So the situation after one round of graph neural network would look like this, that I have a node V and I have these 2 neighbors. And if I do another round, then I might learn that each of those neighbors has 1 more neighbor. Okay, but I can't really learn that this node is the same for both, right? I don't understand at this point here that this node here is really, the neighbor of my 2 neighbors, but both times the same guy. Same thing for, for this 6 cycle. We can see after 1 round, we see this. After 2 rounds, we see this. And, it just goes on like this, right? So it just, in both networks, basically what you learn in a graph neural network is just that you're a node basically in a line. You don't understand that in the left case, the gray node on top in the actual graph is the same node to the left and to the right of yours. And well, here, the 2-hop neighbor to the left and to the right of yours, these are 2 different nodes, right? But you can't distinguish that. That's a direct consequence of the Weisfeiler-Lehman test. Okay.
One interruption. Is there an assumption that the nodes are anonymous?
Yes, the assumption here is the nodes are anonymous to some degree. This is also something you need in the graph isomorphism test, right? You cannot just say, well, the nodes all have names, and then it would be very easy to understand that 2 graphs are the same if you just check the nodes with the same name, whether they then have the same environment. So here in graph neural networks, you usually think of the nodes being anonymous. it can be a bit more than that, right? We could say, for instance, that the nodes are not anonymous, but they only know their degree, or they know some color or something like that, but they don't have IDs. So that part is for sure. And then I would say this is a problem here. Actually, I have but thanks for the question. Actually, this is a good point to ask questions in this part, because I'm still in the part of explaining you sort of how this works and what the limitations are. But I can give you another graph here. So here, actually, the nodes are not 100% anonymous because they have colors. Okay, so we can have white and gray nodes in my picture here. These are two graphs. But if we again do this GNN to it, let's look at this node, one of these two gray nodes. It's very symmetric, but if you look at that, we see here that it has a white neighbor, and that white neighbor has another white neighbor, and that has a gray neighbor, and and that has a gray and a white neighbor. So if I go in this direction of node V, if we go to the right, then you will see that's what you get. And on the right-hand side, exactly the same thing, right? So the animation was looking at both directions, but I only explained the left-hand side. The right-hand side, the node V again, it has a white neighbor. It has two other neighbors, but let's forget about that for a moment. This has a white neighbor as well. This has a gray neighbor, and this has two neighbors, one gray and one white. And you can see the left-hand side, the right-hand side look exactly the same. They're of course very different, because you can see here that this gray guy here is actually yourself again, node V again in this case. Whereas in this case, this is not node V, but this will be node V, right? So the graphs are very different, but a graph neural network can't handle this information. It's not built for that, so to speak. It cannot distinguish those two cases. So if you, for instance, want to distinguish those two graphs, if you want to learn whether those two graphs are different or which graph you have as an input graph, it can never learn that, because the graph neural network would kind of operate on this tree of neighborhoods, and it would see exactly the same neighborhood, left and right. So it can never learn that those are different graphs. So that's in some sense the limitations of graph neural networks. And it's very bad, right? Very simple graphs are not distinguishable by graph neural networks. So those will be exactly the same for a graph neural network, whereas those here will be very different. Okay, so here, for instance, the lower graph, we do have a node here, a gray node, which has two gray neighbors, right? And we don't have that at all in the upper part. So this will be easy to learn for a graph neural network, the distinguishing these two, but distinguishing these two, it cannot do. So what we were wondering is basically with methods of distributed computing, whether we can learn that, okay? Whether we can learn to distinguish those graphs. So that's for the remainder of my talk, how this works. So there's many ways how to make graph neural networks more expressive. And I would say classically, people have run the GNN not on the graph itself, but something like a metagraph of the graph, something like a power graph where you would, when you have n nodes, you come to n squared nodes or n to the 3 nodes after that, and you build sort of a metagraph which makes the connection between all nodes. That's something people have tried. And then they have tried to extend it in other ways. For instance, by port numbers, I get to that in a second, or they have tried random features. Now, what we proposed in our paper is to look at dropouts instead. So this is a DropGNN paper I'm going to explain now. It's a very simple paper. This has been published at NeurIPS just a few weeks ago. So NeurIPS is one of the bigger and probably more prestigious conferences in the area of machine learning. This is again mostly with Andras, but also with some others of my students. So how does it work? What's the idea of GNNs with dropouts? So the idea is to run. Oops, I think I lost my video screen. Can that be? Let me try to share again. Here we were, huh? Oh, guess it works for you as well. I have the two screens, so I can see, I think, what you guys can see.
Yeah, we can see you. Yes.
Okay, good. So, so the idea is to do multiple runs of the same GNN, okay? We do multiple runs while we train the GNN on known data. This is something we do anyway with neural networks. Usually we take multiple runs to train the weights of these neural networks so that with backpropagation. But here we also do multiple runs when we test a network, where we want to know, when we want to, evaluate how good our graph neural network is. We also do multiple runs, not many runs, but maybe 10 or 20 runs. In every run, we remove every node of the network with probability p independently. Okay. So let's say if we do a run, we remove some node, for instance, this node here, that would be the first run. You can see removing nodes changes the network slightly. Okay. And we can do that again. Maybe next run, these two nodes would be removed, and then the network would look like this. And maybe in the third run, no node will be removed. That's also possible since every node is independently removed with probability p. So maybe no node is removed. So if 3 runs, and if we do 3 runs, then we get 3 different values, right? So we get our graph neural network will give us 3 different outputs. And now these outputs we combine in some way. And that's what dropouts are doing. So before we had a problem to distinguish those 2 graphs, but if we had dropouts, it would actually be quite easy. So think, for instance, at some point, this node here, which I marked, is dropped out. This would change the view of node V on the right-hand side so that it now views, to the left side, it only has 1 node and then it stops there. So here it basically stops. It says I have no more neighbors. And to the right side, he has actually 3 nodes and then it stops. So that would be a possible graph this node V basically sees when we run the GNN. Now, since this is, the same node on the left-hand side, if we let this node drop, then this would look like this. And you can see that no matter what you do on the left-hand side, no matter which nodes you drop, you can never ever have this pattern. Okay, now I made a little mistake here. You can never see this neighborhood pattern. It's completely impossible on the left-hand side. And that's exactly the idea here, that if you make a few test runs, eventually in one of those test runs, you might see this pattern. And if you have a good learner, then the learner learns that this is exactly, this must be the right network, the right graph, because it cannot happen on the left graph. And vice versa. Maybe there's a pattern which happens on the left graph and doesn't happen on the right graph. Or maybe there's a pattern which is much more frequent on the left graph than the right graph. So if you have this different distribution of what kind of graphs you're going to see, and that is going to help you to distinguish graphs and to distinguish nodes and to make this problem tractable for graph neural networks. So that's the main idea, I would say. We can look at this other example here that I also showed before. So also here we can, for instance, drop out some node. I drop out, for instance, this other gray node. And then you can see on the left-hand side, what you get is this little triangle of our node inside. Let's say that's our viewpoint here, and it has a little triangle. What we see here on the bottom is basically just a list where you see the gray node coming up every 3 nodes. You have a gray node. The list is infinitely long, depending on how many rounds you do, but you see the gray node from time to time. And on the right-hand side, if you would drop out the gray node, then this would look very different, right? So here we have exactly 2 nodes, white nodes on both sides, and that's it, right? And I argue that this thing that I'm going to have here on the left-hand side, this is in some sense recognizable again. You can never have this pattern on the right-hand graph, no matter which nodes you drop out. Okay, you can never have such a pattern which you can have with this triangle pattern, essentially, with 1 gray node in. That's impossible. So for many, many graphs, we can distinguish graphs, or we can distinguish nodes, can do this classification well if we just drop out some nodes from time to time. So again, what we do is we do multiple runs, and Then we run some sort of an aggregate function again. We check for all these runs. Let's say if you have R runs, we run an aggregate of what was the final value of the graph neural network for our node in that run. And then based on this aggregate, we can say in which graph we are, whether we are in one or the other graph. So we have these aggregates here, and we can do that then. Now, important, this has to be done both in training and in testing. Okay, so this is a bit unusual. Usually in graph neural networks, people would do testing quite often, and then training quite often, but testing they would not do so often. The evaluation, they only run the GNN once and then decide based on that. So here we have to do it multiple times. Good. There's also a little bit of a story about the aggregation. You remember the aggregation function of the neighbors? That's also helping the GNN. Here's an example of two nodes V in two different graphs, and they have neighbors, let's say gray and black neighbors. And you can see, of course, it's very different, right? On the left-hand side, the node has 2 neighbors. On the right-hand side, the node has 4 neighbors. So these are very different graphs, or very different nodes for sure. But if we do mean aggregation, this might not be so easy. So let's say if you take values for the colors, if you say the gray color is now value 0, and the black color is value 1, as in the picture, then you can see if you just do the mean, when you aggregate the values of your neighbors, then the left picture will give you a mean of 1/2, right? 0 plus 1 divided by 2. But the right picture is also 1/2 because it's 0 plus 0 plus 1 plus 1. That's 2 divided by 4, right? Which is also 1/2. So these are not distinguishable, these two situations for a graph neural network usually. But with dropouts, this is easy. Let's say if we have a dropout in our neighborhood, then immediately the mean here becomes 2/3, right? 2 1s and 1 0, which is a value we cannot achieve at all on the left-hand side, even if you have dropouts, right? No matter which neighbors drop out here, the only values we can achieve are 0.5 when nobody drops out, or 1 and 0 if one of the two drops out. So you immediately know the difference, and the learner can learn this, and they can understand that that they are now really in this graph and not in this graph if they see the value 0.66 at some point as an aggregate of the neighbors. Good. I want to have a bit of time at the end for discussions. So maybe if I go for another few minutes, that should be okay. Satya?
Yes, it's a break after your session. So
okay, also that. So we did a bit of analysis. So we are in some sense, algorithms guys, distributed computing guys. We did a bit of analysis in the paper, in this NeurIPS paper I mentioned before. We studied, the likelihood of some dropouts. Of course, there's many different dropout combinations. You could have 2 to the n different dropouts if you have n nodes in a neighborhood or in a graph, because every node can drop out or cannot drop out. That's a lot of combinations. If you have to learn all these combinations, you have to learn a lot of things, right? You have to see exponentially many runs to learn just what is possible. And that's not doable in many situations. So you don't want that. So we usually just restrict ourselves to 1 dropouts to make it much easier learnable, so that we only have a few runs. Now, if you have just 1 dropout, you have n nodes, then you have just n different runs that you have to test for 1 dropouts. So that would be an advantage. So you always have 1 dropout and you check. So you never have this basically. And you check what you have there. And so if you do, usual Coupeau collector argument, if we do n log n runs, then, or the usual Chernoff argument, I should say, maybe, we observe every 1 dropout with high probability even. So that's to make it fast. But there's also limitations. So there are graphs actually which cannot be distinguished with 1 dropouts only. So if you have all the dropouts, all the 2 to the n dropouts, that you can distinguish everything. But if you only have 1 dropout, this could be a problem here. And let me see what I have here. So, I have 1 neighbor dropout, for instance, in those 2 graphs. And what the GNN sees is exactly the same on both sides. So, and one can make an argument that the distribution of things the GNN sees over the time is always the same on both the left and the right graph, and that's why you cannot distinguish these one dropouts. But there's another theorem in the paper. If you would add port numbers, that's also a concept which is known in distributed computing, but also in graph neural networks, then we could actually distinguish any two graphs from one dropouts. I come to port numbers in a second. Let me go slightly at the end, into the more practical side. So what machine learners do, they usually do benchmarks. Okay, so they test their ideas on benchmarks. There's many benchmarks they have for graph neural networks. I would say they're all very bad. Okay, none of them is really good, unfortunately. So the famous one is the CORA benchmark. This is something which scientists can probably relate to. The CORA benchmark is a benchmark about papers and citations. So every node in the graph is a paper publication, and the edges between the nodes are citations. So if one paper cites another papers, we make an edge between those. And the CORA benchmark tries to figure out in which area a paper was published. Okay. Actually, it's only computer science, as far as I remember. So in which area of computer science is a paper published? So it has, every paper has some information about it. It has a content information, it has a paper ID, and it has, for instance, sort of like the title information of the paper, what kind of words it uses there. And it has other keyword information and stuff like that. And then it has also, we also have citations. So we have content information, we have citation information. That's the information of a paper, those two things together. And I would argue that this is in some sense a very bad test for graph neural networks, because it's not really testing the graph much, right? So if I just gave you not the graph at all, if I just gave you a table, and the table would have, the title of the paper, and maybe the keywords of the paper, and maybe some information about the neighbors in the graph, but not who the neighbors really are, but just, let's say, what labels the neighbors have, or what keywords or title they have. So I could arrange all this in a table like this, all the papers I could arrange in a table, and I would argue to understand that this paper here, for instance, is a crypto paper itself. You don't need the graph information at all. All you need is kind of the label neighbors, what keywords they have, something like primes already kind of says that this is probably a crypto paper. So you have a lot of information already there. And problems like the one I explained before, where you have to really understand the graph, you have to understand the graph structure, they don't really happen in this benchmark. And unfortunately, this is true for many benchmarks. So what people test there, I would say, has not much to do with graphs in the classic sense, okay? Because all the graph information is sort of not relevant when you test this. Okay. So there is one dataset which sort of makes sense, and that's the QM9 dataset. That's a molecule distinguishing dataset. So you want to distinguish certain types of molecules. And molecules, the graph does matter, right? Because depending on how you connect your atoms with each other, it becomes a different molecule. It's not just, the graph information really matters there. And you can see here is is for several different tests this data set gives you. I'm not a chemist, I don't know what these tests mean. You have like classic GNNs, how well they do the test. And what you see here, the numbers are always the errors. So this in 35% of the cases, it would label things wrongly. Whereas the DropGNN here is much better. Only in 7% of the cases you classify wrongly. And you can see it makes a big difference. This dropping out makes really a big difference. Another method which is also pretty good here and sometimes has the best results is the PPGNN. But the PPGNN is massively more complicated than the DropGNN. it really operates on some sort of meta graph. So, you know, when the work we have here is really order of n in some sense, then here the work we have is something like is much more. So in some sense, we kind of get to the same level as these guys, but with much less work. So that's why people like myself think that this idea of cutting down the graph, dropping nodes might be a good idea. There's other extension ideas. Let me quickly tell you about that. So the port numbers I mentioned before, that's something people do in graph neural networks. There they add basically information to the network. They say, well, maybe we can distinguish things better by adding port numbers. But even for port numbers, this would be a bad example here, because one can easily find graphs which are not distinguishable with port numbers. Sometimes they put on angles. So the idea is that, let's say if you have a chemistry example and you have something like water, the water molecule, then you have something like an angle information really, but also there it can be shown that the angle information does not really help. In the worst case, cannot distinguish things, even if you have angle information. And for many graphs, of course, you don't have angle information. You don't know what angle your neighbors have between them. Or they add random features and whatnot. So many of these things have been tried, but none of them worked really well. Good. So this is just as a final almost slide, a very bad example here, which has two graphs which are hardly differentiable for even the best methods we have out there. So one is called the Rook graph here, and the other one is called the Shrikande graph. The Rook graph is just what the chess piece Rook how it can move on a 4x4 matrix. Good. You know, we did a bit of comparison of these things. So this is the newest paper we have in the pipeline. What kind of method is better or worse? Like how much is dropping things better than doing metagraphs? And can we build a sort of a theory there to understand how difficult or how different these extensions are and which ones are more powerful than another one? I'm not going to explain that. It's unpublished work. So let me finish with open questions. So, of course, what I just mentioned is the last thing. There's a bit of theory one could do here. One could probably characterize graphs that can be distinguished by extensions and cannot be distinguished by extensions. Then there could be experimental questions looking in particular for applications where the graph structure is really crucial. Unlike the CORA benchmark with the citations I showed you, where it actually matters what graph you have. This is certainly true for traffic graphs, I would say, that it matters what the graph looks like, and for molecules, but for many other things people have looked at, it doesn't matter so much. And yeah, maybe there's similar approaches in other deep learning areas. There are similar approaches for something I call algorithm learning, which might be interesting. These are some things we are trying these days. Good. So with this, I would like to finish here. I want to thank you for staying for this long talk, and I would be happy to answer some questions.
Yeah. So we have more than 5 minutes for question and answer sessions. Okay. Yeah. So yeah, anybody from audience wants to ask a question?
I should have told you to write in the chat as well, because I was looking at that during your talk, but nobody wrote anything, I think.
Yeah, yes.
Just one little, I do not work, I do not know much, but just a maybe very naive question, that dropping out a node. So in a classical algorithms, or in what do you mean by that? Something like a pruning the problem complexity, or I just Philosophically,
So
what does it mean?
Yes. So here we really want to change the graph a little bit. That's what dropping out means here. And dropping out really means deleting the node and deleting all the edges this node has, right? That would be dropping out here. So, so that changes the graph, of course. But the hope is that if we make a few of those changes, that this gives us some power to understand the graph better somehow. That's the idea. However, some people said they don't like dropping out the nodes. They would do something slightly different. For instance, they would just not deleting the node, like literally deleting the node from the graph, but maybe just removing the information at this node, something like this, to say the node always sends you a 0. When it sends you a message, it always sends you a 0. That's also something which could be called dropping out. So there's a few of these possibilities we do there. And we really do it to make sure that we can then distinguish graphs which are otherwise not distinguishable by graph neural network methods, right? So like the examples I have here, since graph neural networks cannot distinguish those graphs, they are not so smart in some sense, right? They cannot learn everything we want them to learn. And this is our method to make them learn that.
Mm-hmm.
I hope this helped a little bit.
If suppose like, you have weight calculation and to distinguish the bit among them. So if they have equal weight, then the average could be the same. The distinguishability may not be possible.
Yes, yes, very very good example. Exactly. So if you just average things, sometimes you cannot distinguish things very well, right? And that's of course it would be better to not average, but that's also something you can study here. So many things could be done here. I would say I'm a bit skeptical about this idea of averaging this information of all your neighbors all the time.
Mm-hmm.
The people who did graph neural networks first didn't have another idea, because usually when you have a neural network, you have a fixed number of inputs. And now if you average all your neighbors, let's say this is this average or the sum of all your neighbors, right? Then it's always, no matter how many neighbors you have, it's always the same number. But if you don't average and if you would have the information of all the neighbors, then how do you do that when somebody has 3 neighbors and somebody has 17 neighbors, right? It's not clear how to feed this into this neural network, because you only have a designated space for this information here in the neural network. Yeah. So averaging or taking the sum or taking the max, these are simple ways how to do that, but maybe there are much better ways out there. We just don't know yet.
Yeah, maybe corollary to this is that is there any a way, I mean, I said that, based on the common knowledge of the graph, in the course of iteration, can there be a decision on which node is to be dropped?
Yeah, so we don't do that, but you could do that as well, right? You could do something like a more deterministic version of dropouts, where you don't drop nodes, don't drop nodes randomly, but you drop nodes with a bit of algorithm smartness. Sorry, we haven't done that, but this is something we can you can definitely consider. Yeah.
Okay. Thank you.
Thanks. Yeah.
Professor Roger, can I ask a question?
Sure.
Yeah. So if we don't drop out, then let us say that we are inferring at node some value. And if we drop out and then with the DropGNN, you get some other inference.
Yes.
So there is a difference there, right? So we could call that some kind of error. So now, given some kind of error, can we kind of design how many dropouts and what kind of dropouts I can?
Yes. So in the paper, that's all correct and well said what you said. Of course, if you feed the graph without dropouts, you get some value. If you feed the graph with some dropouts, right, you remove some node X, for instance, then you get this different value probably for that. And one has to, what we do here, we just aggregate all these values and we say, based on these values, we now make the following decision. But there could be better options to do here. But important is this part here that you said that that the values will be different. The hope is in some sense that for one graph, let's say G, we can reach, let's say, this value V prime. But for a graph G prime, no matter what we do, no matter whether we drop out something or we don't drop out something, we never get the same value V prime, okay? And that would help us to understand that this must be the graph G prime we're looking at here, if we want to distinguish graphs.
Mm-hmm.
Maybe there was another question inside your question, but I might have forgotten it.
I think this was the question. So this leads me to think that this question is regarding the global questions, not the node level questions. Okay.
Yes, this both, I would say. I think for me, the global thing is a bit more easy to understand, but the node level things have the same problems as well, right? You might want to say which type of node is it? What I said before, man or woman, for instance, right? It could be 0, 1, or even values between 0 and 1 if you want to be very modern. And you could say you want to know that, right? And the dropouts could help you maybe understand that well. For instance, I don't know, the social network of women might look a bit different than that of men, right? So if you train this, I have no clue about the sociology behind this, but you could say, you know, maybe some have more friends and some have tighter friends or something like this. And then you can figure out whether it's rather a man or rather a woman based on these things, on the network characteristics. And then in the end, there's a value which maybe women can achieve with dropouts, but men cannot achieve with dropouts, something like that.
Awesome.
Yeah.
Thank you.
Thanks. Yeah.
Okay. So I think we can. So let me. We have a few more minutes. Maybe we are exceeding by 5 more minutes. So
one small observation. This also seems like very similar to, I mean, at least philosophically, getting synthetic data, right?
Yes. So we test a lot with synthetic data as well, because what I said before, the benchmarks which exist in machine learning on graph neural networks, they don't help us so much. They are not so good. So we train a lot with synthetic data. For instance, you know, I give you 2 types of graphs. One graph contains a triangle somewhere, one graph doesn't contain a triangle somewhere, and we synthetically make up these examples. And then we test whether our methods work on these examples. And of course, for such synthetic data, this DropGNN, for instance, would be very, very good. But other people have developed other methods in the meantime. So this is only, as I said, was only published in December, just a few weeks ago. But since then, we have seen a few other papers showing up on arXiv where people start to try to understand what is possible with other methods in this context. Yeah.
Thank you.
Thanks. If there's more questions, you know, you can just drop me an email if you want. Be happy to answer, of course, if somebody has a question later on or wants to know something else. Yeah.
So maybe you have 2 more minutes, 1 more minute for a question. So let me ask you one question. Okay. So in this graph dropouts, I was trying to understand how is it actually distributed? Is it happening in a distributed manner, or is it centralized?
The dropout itself, or
yeah.
So far we do this completely centralized. So we run, let's say, the machine learning algorithm on some machine. It gets a graph and it does the dropout centrally. And like that, we can, for instance, also guarantee that we have exactly 1 dropout if we want to guarantee that easily. Otherwise, if you do it in distributed manner, that's slightly different. And it would probably be possible to run graph neural networks in a distributed manner because it's kind of the same thing as distributed computing on graphs, but we don't do that so far. It was mostly about what can we do, what can we not do so far.
Okay. Yeah, so I was just trying to understand, yeah, the distributed computing aspect of this algorithm. Is there any, or in general, the graph neural networks that we can work in distributed manner, but in this algorithm, right now it's centralized. Is it correct?
Yes, yes. So I would say graph neural networks are like distributed algorithms in some sense, right? They're the same. They have the same feeling to it, but the running we do it completely centralized so far. We just simulate the distributed nature of it because it's because the speed was so far not our main concern. It was expressibility. Yeah.
Now we're looking at speed. Yeah. And the other thing is, right, at least the problem that you try to solve at a high level is basically you're trying to see graph isomorphism, right?
I would say that's part of it. I mean, if we could graph isomorphism with learning, you could also see it like that. But it's really a bit more than that because usually the nodes do have some features, right? It's not that they have no features. Graph isomorphism, usually the nodes really are completely anonymous, and you have to understand whether two graphs are the same. Here we usually have something like original colors or, like some IDs in the sense, maybe not IDs, but in the sense of, the nodes have a type, they're either male or female or something like this. I think these things we do have usually. So it's a bit different from, let's say, real graph isomorphism. And the main difference to real graph isomorphism is that we're not looking for an algorithm which can solve it. We look for things which can learn it, right? So the hope would be to understand, better. Like if you have some problem, but we don't quite know why a node is of this or of that type, right? We just have lots of examples which would tell us this is of this or of that type, or lots of graph examples which would tell us this is, a molecule of this type and this is a molecule of that type. But we maybe don't know why it is such a molecule. We could say one can be used for, one is medicine and the other one is poison, right? We don't know, which is which. We just have tested. For some reason, we have understood that this is a poison molecule, this is a medicine molecule, and now we want to understand why is it really a medicine? Why is it a poison molecule?
Yes.
Yeah.
Okay. So yeah, probably. So thanks. Maybe we should stop here because we are going into the break.
Yeah.
Okay.
Thanks a lot. Yeah.
Yeah, thanks. Yeah. I think any questions, probably they can always email.
Yes, yes, definitely. Yeah.
Email. Yeah. Yes. Thanks for the nice talk. Okay.
Thanks. Yeah.
Thanks. Yeah. Okay.
Now, yes, sir. Yes, sir. Thank you, sir. Now, I'd like to take an opportunity to thank Professor Roger, Professor Satya Perry, faculty members, and all the participants for joining. With this, we come to the end of the 6th speaker session. We'll be having our next session at 4 p.m. Do kindly join. I, Shwet, signing off from the 6th speaker session of 18 ICDCIT 2022. Thank you so much.
Thank you.
And a warm applause for the speakers. Okay, here in the online setting. We can give reactions on Zoom, actually. Yeah, thumbs up or claps.
Yes, thanks. I got many reactions actually on Zoom as well, so thanks a lot.
Thanks.
Anyone hear the claps?
Yeah, maybe you can.
For both the speakers, yes. Thank you. Nice. So maybe you can take a break.